अच्छा चलिए ठीक है Lubena, we were going to start Born-Haber cycle ठीक है and I had told you कि Born-Haber cycle जो that's specifically used to calculate this thing. It's used to calculate your lattice energy. And what was lattice energy? It was the energy that was needed. Where is it? This one. It's the energy that is released when 1 mole of ionic lattice is formed from its gaseous ions. So your gaseous ions, they would join up and they would form 1 mole of ionic lattice. So that energy that is released, that is your lattice energy. And this value had some significance. What it would do is that it would give you an idea of how strong the lattice is. But the problem with this value is you can't calculate it directly. And the reason you can't calculate it directly is because it's very hard to actually find these gaseous ions and then join them up to form the ionic lattice. I mean, performing this reaction in the real world is kind of difficult. So to measure lattice energy, an indirect method is always used, and that involves the Hess cycle. ठीक है, Lubena, is this clear?
Yes, sir.
So now just a brief overview or background of what the Hess law is. Now your Hess law states that the enthalpy change delta H of a reaction is the same no matter what path is taken. So no matter which path or route is taken. So, for example, if I have a reaction that's happening and it's carbon reacting with oxygen and it is producing carbon dioxide. So that is one reaction. And that particular reaction is going to have a certain enthalpy change. Let's call that delta H1. Now, to make carbon dioxide, this is one path. I mean, your starting point is this one, and your end point is this one. You basically want to make carbon dioxide. And what you could do is you could break this reaction into two steps. You can either first convert carbon into carbon monoxide, and then carbon monoxide can be reacted with oxygen, and you can then convert it into carbon dioxide. So that you can break it into two steps. So there would be one reaction where carbon monoxide would be formed, and there would be another reaction where that would be your that would be your third reaction, where carbon monoxide is converted into carbon dioxide. The route doesn't really matter. As long as you're making carbon dioxide, the enthalpy change would be the same, which gives you this relationship that delta H1 is going to be equal to delta H2 plus delta H3. Because at the end of the day, you're breaking and making the same number of bonds. So which is why the enthalpy change would pretty much be exactly the same. Okay, is this clear?
Yes, sir.
So there's path 1, and then there is this other path. And you can always have indirect routes for any reaction. The good thing about Hess law is that it connects three completely separate reactions together. A Hess cycle does that. For example, over here, you had three separate reactions. You had carbon reacting with oxygen and it was producing carbon dioxide. You had another reaction where carbon was reacting with half oxygen molecule and it was producing carbon monoxide. And there was a third reaction where carbon monoxide was reacting with oxygen and it was producing carbon dioxide. So there were completely three separate reactions, but you found a relationship to link those three reactions together. And what the advantage of this is that if you know the enthalpy changes of two of the reactions, you can figure out the enthalpy change of the third reaction by just plugging in the values. And if delta H3 is unknown, this one is not known, you can find delta H3 by using delta H1 and delta H2. Okay, so is that clear?
Yes, sir.
And that is exactly what we're going to do for the lattice energy. That if lattice energy is not known, but you know other enthalpy changes, you can connect them together in a Born-Haber cycle, which is a Hess cycle, and you can find lattice energy. So this is how all Born-Haber cycles are going to be formed in this way. So you're going to start off with, you can start off, remember it's a cycle. So a cycle doesn't really have any start point or end point. And also remember, I'm sticking to this. You can have any two paths. For example, I chose these two paths, but the relationship would still hold if I had chosen any of the paths. For example, I could have chosen this path that I'm going from carbon monoxide to carbon dioxide. This is my path number one. And the other path is I go from the other side and I form carbon dioxide, right? So I can, as long as the starting point and the end point is the same, the two paths are going to be the same. Like if I'm starting at carbon monoxide and I'm reaching carbon dioxide, so this is one direct route and there's this indirect route. So if I equate the two paths, it's going to be delta H3. That's the direct one. And the other, if you're going opposite in the direction of the arrow, this would be minus delta H2. And that one would be, the top one is delta H1. Okay? But remember, this is exactly the same relationship. I mean, this relationship and this relationship is exactly the same. Lubana, is this clear?
Yes.
Plus, another thing is, you can do a lot of things with this. What you can do is, the easiest one is, if you start at this point and you come back, you go all the way and you reach this point again, your enthalpy change would be zero. Because you're coming back to the same thing. So, that would give you the same thing. It's going to be delta H2. Then it's going to be delta H3. This one. And then you're going in the opposite direction of delta H1, so that's going to be minus delta H1. And the enthalpy change of this particular path would be zero. Why? Because you started at that point and you came back to that point. So that means overall there is no energy change because you ended up forming the same thing. So that's another way of equating things. Okay, so is this clear how to use the Hess cycle?
Yes, sir.
So the Born-Haber cycle is, okay, and remember it's only ionic compounds. So Born-Haber cycle is, let's do it for MgCl2. Now, and again, you can start at any point. I usually start with enthalpy change of formation, which is elements. So it's Mg and Cl2. These are the two elements. And they're reacting together to form MgCl2, which is a solid. Okay, that's your enthalpy change of formation. You can find this enthalpy change in the lab. It's magnesium metal reacting with chlorine to form MgCl2. So that's, you can find this value in the lab. And most of the time, this value would be given in your questions. Now, the indirect route is, we're going to try and figure out how to form MgCl2 stepwise. What is solid MgCl2? Solid MgCl2 is an ionic lattice. It's Mg2 plus attracted to Cl minus 1, which is then attracted to Mg2 plus and so on. So it's an endless lattice of positive and negative ions all joined up. In this case, it's going to be 1:2. For every one magnesium ion, there are going to be 2 Cl ions in the lattice. But positive and negative ions would all be connected together, joined up. So what's the first step? If I want to make an indirect path, the first step would be atomization. Because my elements are right now bonded to each other. Like magnesium is metallic. So what I'm going to do is I'm going to convert it into gaseous atoms. Like I'm not going to touch Cl2 right now. So this is enthalpy change of atomization of Mg. So I need to separate my magnesium atoms. I need to break their bonds because over here the magnesium atoms are no longer together. So I need to separate them. I need to atomize them. I need to break the metallic bonds, and that's enthalpy change of atomization of Mg. Is this clear?
Yes, sir.
So now I've broken the Mg atoms to get Mg bonds. Next step is I'm going to break the Cl-Cl bond. So that would give me two Cl gaseous atoms. So basically the are bonded together. So I'm going to break those Cl-Cl bonds. So that's basically the bond energy of this thing. So I'm going to break the Cl-Cl bond. So this thing over here, this root so far is, what is this? So this one is atomization. So this is atomization. Next step is, in the lattice that I'm planning to form, the Mg is in the form of ions and the Cl is also in the form of ions. So I'm going to ionize these substances. So first is, let's make Mg lose the electrons. So it would form Mg2 plus gaseous. And it would lose 2 electrons. Nothing happens to Cl yet. So Cl is still gaseous. What is this step called, where Mg loses 2 electrons?
The first and second ionization energy of Mg.
Okay, so that's your first and second. Just one second, let me change the color. So okay, so that's your first and second. Ionization energy. And then Cl is the one that's going to gain those 2 electrons. So it's going to be, next step would be, Mg has already lost those 2 electrons. So Mg as it is, 2 plus, gaseous. And Cl would be the one that would be gaining those 2 electrons. So it would become 2Cl minus 1. This would be the electron affinity of the Cl atom. So it's going to be the electron affinity of Cl, and that's going to be multiplied by, it's going to be multiplied by 2. And then you have the last step, which is going to be the lattice energy, where those gaseous ions combine and they form a lattice. So that's your lattice enthalpy. Okay, is this clear?
Yes, sir.
So basically what you have to do is you have to atomize, and then what you're going to do is you're going to ionize. I mean, this step is, this is where ions are formed, and then the ions get together to form the lattice. So what you have to be careful about is that, as a one by one, all the values would be provided to you except for lattice energy. So it's going to be one path equal to the other path, and you can figure out the value of lattice energy. What you have to be careful about is enthalpy of formation is usually given in the question. Enthalpy of atomization is also probably given in the question. If during atomization you're breaking just a bond, then it's going to be bond energy. Like if it's Cl2, then it would be bond energy of the Cl molecule, or the Cl-Cl bond. If there was an oxygen molecule over here, you would just break the oxygen-oxygen double bond. But remember, bond energies can only be used if the substances are gaseous. TK, is this clear?
Yes, sir.
Then the ionization energies are also given in the data booklet. The electron affinities are not given in the data booklet, so they would probably be provided to you. And the lattice energy is not given at all. So you have to draw this Born-Haber cycle, and you have to be very careful about. I mean, these are. I'm just going to write a few points that you have to be careful about. One of them is, be careful about moles. So you have to be very careful about moles. For example, Cl over here, electron affinity of Cl was being multiplied by 2. So if you miss that point out, your lattice energy value would come out to be incorrect. ठीक है, clear है?
Yes, sir.
And then minor things like if this is first plus second ionization energy, you should know that even though there are two Cl atoms forming, but you're just breaking one of the bonds. Okay, so it's 1 mole of bonds being formed. So you have to be very careful with the moles, like what quantity of each thing and each step, what's happening in each step, how and what is the quantity of that thing happening. The second thing is remember when to use bond energies. So be careful. Bond energies can be used only if substances are gaseous. वो जगह ही कोई नहीं प्रोजेक्टर नहीं वो नहीं है अभी नहीं यूज करा पहले करा था ठीक है चलो बेना remember bond energy would be used if substances are gaseous. But अगर यही चीज़ ना exactly if they had done it for iodine MgI2 then यहाँ पे you can't use bond energy for I2 ठीक है because I2 की state क्या होती है it's the element is solid ठीक है is this clear.
Yes, sir.
And the final thing is you have to be very careful with be very careful with your calculator. Okay, you got to be very careful with your calculators because you have to add and subtract a lot of things when you're doing the calculation. So a minor mistake with the sign or with any of the values, your answer is going to come out. It won't come out to be the correct one. So you have to be very careful when you're doing calculations with this. So I'm going to draw another Born-Haber cycle. Let's draw it for another ionic compound. Let's call it. Let's do it for aluminium oxide. Now the moles are going to be very different in aluminium oxide. Like everything has to be. So first thing, start off with enthalpy of formation. So you've got aluminium, which is a solid element, and oxygen, which is a diatomic gas. And these two are joining up. And they are forming Al2O3, which is a solid. Okay. Now, in enthalpy of formation, 1 mole of a substance should be formed. So that means there would be 2 Als and there would be 3 by 2 oxygens, right? Because you need it's 1.5 oxygens, right? Okay, is this clear?
Yes, sir.
I said then you have one second. I said then you have you're going to figure out the other route. First thing, you atomize. So atomize aluminium. It's going to be 2 Al gaseous atoms. Keep oxygen as it is. I mean, you can combine 2 steps together. Like you can do the atomization in 1 step. Because you'll be asked to draw this sometimes, so it's better to actually write down every step, every single step that you're doing. So there's 3O2 gas, 3 by 2 O2 gas. So this is enthalpy change of atomization, but it's going to be multiplied by enthalpy of atomization of Al, and it's going to be multiplied by 2. Okay, so the moles are going to be they're going to be 2. Next one. Next is you break the oxygen-oxygen bonds. You can use bond energies over here. Aluminium would be as it is, nothing happens to it. How many oxygen atoms would be formed? I think it's going to be 3 oxygen atoms, TK. Rubena, is this clear?
Yes, sir.
So how many bonds are you breaking? You're breaking 3 by 2 oxygen double bond oxygens. So open the data booklet and you can find the bond energy value for this. Next step is ionization. So aluminium should lose 3 electrons. It should form 3 plus ions. So it loses those 3 electrons, but it's not going to be 3 electrons, it's going to be 6 electrons. And there are 3 oxygens, which right now we haven't done anything to them. So what step is this?
The first, second, and third ionization energy of electron.
ठीक है, but it's also so it's the first plus second plus third. But it's also being multiplied by 2. ठीक है? And then you have the next step, which is going to be so what's the next step? It's going to be aluminum has already lost the electron, so it's 2Al3 plus gaseous. Now the 3 oxygens are going to gain the electrons to form -2 gaseous oxygen ions. So what is this step?
The electron affinity of O1 negative plus O2 negative multiplied by 3.
It's electron affinity of oxygen and electron affinity of O minus 1. ठीक है, it's oxygen gaining 1 electron, then O minus 1 gaining 1 electron. And that's going to be multiplied by 3 because we've got 3 oxygens doing that. ठीक है, is this clear?
Yes.
Up here you have the final step, which is the lattice. That's your lattice energy. Now in this cycle, it's the same cycle exactly, nothing different. It's the same one, like the one that's before it. So it's exactly the same, but you have to be very careful about the values that you're putting in and how many moles are being used. So we're going to try and do a few questions on this. 1 second. So let's try and do a question. Okay, so I've got this question over here. And in the question, where's the question? Achha, so you can see the question is asking for the lattice energy of potassium oxide. So we would have to make the Born-Haber cycle of potassium oxide. So it's going to be potassium, that's the element, oxygen, which is diatomic, and together they are forming the ionic substance, which is K2O, right? And that is a solid as well. This one is a gas, and this over here is a solid as well. Okay, so the enthalpy of formation is given. That's so it has to be 1 mole. So this would be half, and this would be 2. So the value is given. This value is given as minus 361. So I'm going to write this down. Okay, Lubena, is this clear?
Yes.
As the next one, start with atomizing the substance. So it's going to be 2 potassiums turning into gas, plus the half O2 right now doing nothing. So what's the atomization of potassium? It's given as plus 89. So that's going to be plus 89, but multiplied by 2 because you've got 2 potassiums. Then you want the oxygen bonds to be broken. So break those oxygen bonds. So 2 potassiums gaseous as it is, and you get 1 oxygen atom in gaseous state because you've broken half the bond, half of oxygen molecules. So that's half the bond energy. So there would be, in the data booklet, this value is given as 496, but into half because you're doing it for half moles. ठीक है, is this clear?
Yes.
अच्छा, फिर ionization वाला step. You've got to ionize potassium, so it's going to be, so you got to ionize it, so it's going to be 2 potassiums plus 1 losing 2 electrons, and the oxygen is as it is. So the ionization energy is not provided, so it's probably in the data booklet. So I'm just going to open the data booklet. So on the second or third page, I think ionization energies are provided. This one. So potassium is over here. Remember, the first column is the proton number. Okay, people sometimes what they do is they think this is the first ionization energy. Be careful that the first column is the proton number. So ionization energy of potassium is 418. So it's 418, but multiplied by 2 because you've got two potassiums. And then you have oxygen that would be gaining the electron. So then you've got potassium already lost those electrons. 2 electrons gained by oxygen minus 2, forming oxygen minus 2. So this step is the electron affinity of oxygen is minus 141 plus 798. So it's minus 141 plus 798. And we just have one oxygen, right? And that's your final step. That's your lattice energy. Now what you have to do is you have to solve for lattice energy. So one path is equal to the other path. So I'm going to make two paths. One is this one, and the other one is this one. So we're going to use those two paths. So it's going to be minus 361, which is basically equal to the whole other thing. It's plus 89 into 2. And then it's plus 496 times half. Then you've got 418 times 2. Then you got minus 141. Then you have plus 798. And then finally you have lattice energy. So you solve this and tell me what the answer is.